All right, so in the last video, I talked about position and velocity and showed like kind of an intuitive explanation of why the integral of velocity was displacement, and that gave us a net change in position. I related that to the net change theorem, which is just sort of a slight generalization of that idea. Generalizing that a little further brings us to the first part of the fundamental theorem of calculus. The fundamental theorem of calculus has two parts. The first part is the part that most people think of, and the second part is a little more technical. I'm going to show you a proof of the first part, but I'm going to show you a proof of the first part that relies on the second part. So I'm introducing the first part now. I'm going to show you how to use it. But later in a future video, I'm going to introduce the second part, and then I'm going to prove the second part, or roughly, do sort of a sketch of a proof of the second part, and then I'll sketch the proof of the first part. So proof of this is forthcoming, okay? You've already seen sort of like some of an idea of why this might be true based on this position and velocity argument, but yeah, we'll see more details on that later. So what this is saying is just that if you have a function f, and as long as it's continuous on a closed interval a to b, if you take an antiderivative capital F, it doesn't even have to be the the indefinite integral. You don't really need the plus c on the end. It doesn't have to be the general antiderivative. Just one antiderivative for this lowercase f. Then when you take the definite integral of f from a to b, this can be evaluated by simply evaluating the antiderivative at the end, at the limits of integration b and a, and then subtracting one from the other in this way. So capital F of the final value minus capital F of the initial value, like that. And that is a much quicker and easier way to evaluate definite integrals, easier than all the things we've been doing so far, even easier than the geometric formulas in some respects, and certainly more widely applicable. So let's do some examples. For our first example, let's look at an integral of just a polynomial. Let's go from 1 to 4. I'm going to take x squared minus 2x minus 3. Okay, sure, we can find an antiderivative of this polynomial, okay? What this theorem is saying is that if I can just find an antiderivative for my integrand, which would be this polynomial here, x squared minus 2x minus 3, that's lowercase f. If I can find an antiderivative, then all I need to do is evaluate it at 4 and at 1, and then take the difference. And that will be the value of this definite integral. Holy cow. So much easier than doing a limit of a Riemann sum. So all I've got to do is find an antiderivative. Let's write that down first. I need to perform the anti-power rule here. So I'm going to raise that up to 3, and then I'm going to divide by 3. There's a 1/3. Minus, okay, now the antiderivative of 2x is going to be x squared. We're pretty familiar with that one. And then minus the antiderivative of 3, which will be 3x. I don't need to bother with a plus c on the end. Now what I'm going to do is take that, and I basically want to evaluate this at 4 and evaluate this at 1 and take the difference. And there's a special notation for that. If you do this, if you put a vertical line over here, just a vertical line like that, and put a 1 at the bottom and a 4 at the top, this is a special notation which basically means take this function and then evaluate at 4 and evaluate at 1 and subtract the results in that order. So that notation just means we're going to do 1/3 times 4 cubed minus 4 squared minus 3 times 4. Take the value of that and subtract from it 1/3 times 1 cubed minus 1 squared minus 3 times 1. So there it is. So that's our antiderivative evaluated at 4, evaluated at 1, and we're subtracting them. And the result of this, do some arithmetic on that, -3. And that's it. That's how you use the fundamental theorem of calculus to evaluate a definite integral. So much easier than all of that limits of Riemann sums that we were doing last time, right? So I hope you appreciate that. Let's do a few more examples. Let's do a trigonometry one. Let's do sine of x. We can find the antiderivative of sine of x. That's pretty easy. Let's go from 0 to pi. Okay, dx. So an antiderivative for sine would be negative cosine, right? We've talked about that before. The derivative of cosine would be negative sine. So throw another negative on there to cancel out the first one, and you get back to positive sine. So that's an antiderivative. We want to evaluate that antiderivative at pi and at 0 and subtract. So we're going to have negative cosine of pi minus negative, so becoming a plus, cosine of 0. But cosine of pi is -1, so we have -1, and then plus cosine of 0, and cosine of 0 is +1. So this is -1 plus 1 is 1 plus 1 is 2. So what this means, just for context, is that, just so you understand, if you take the sine function like this, here's 0, here's pi, this is your xy axis, it means that the area underneath the sine wave between 0 and pi is equal to exactly 2 units. Exactly. Which is pretty fun. Kind of surprising, because this area, is not clearly, it's not obviously, it's certainly not like a geometric area that you could calculate, but that's equal to 2. All right, so let's look at one more example using sine of x. What do you think will be the value of the integral from 0 to 2 pi of sine of x? So if we go from 0 to 2 pi, right, 2 pi is over here, 2 pi. So based on the graph, think about what the answer should be. We have 2 units of area here between 0 and pi. Between pi and 2 pi, we have the same exact shape, but reflected beneath the x-axis. This should be negative 2. It should be 2 here and negative 2 here. So it should add up to 0, right? Well, let's double check. Okay, well, let's take our antiderivative, negative cosine of x, evaluate it at 0 and at 2 pi, and then subtract. We're going to do negative cosine of 2 pi minus negative, so plus, cosine of 0, and we get, well, cosine of 2 pi is 1, so this is going to be negative 1 plus cosine of 0, which is 1, and that is indeed 0. So just confirming what we suspected, the net area there from 0 to 2 pi is 0. So this is just a few examples of how to use the fundamental theorem of calculus. In the next video, I'll go over some exercises. I'll give you a chance to try this on your own, and then I'll give you the answers, and you can check yourself. And then I'll continue the lesson after that.